Every second, trillions of data packets traverse a sprawling grid of dark fiber, spanning oceans and continents to reach specific endpoints. The logic steering this global traffic is called routing. Operating at Layer 3 of the OSI model, routing relies strictly on IP addresses to navigate between disparate networks. This is distinct from switching. A switch operates at Layer 2, using MAC addresses to move data within a single local network. A router's job is to bridge the gap between separate networks. When a packet is in transit, it does not carry a pre-calculated map of its entire journey. It carries only a destination IP header. To process that header, it hits a router. A router is a specialized computer equipped with a CPU, RAM, and an operating system dedicated entirely to parsing incoming IP addresses and determining the next step. No central server controls the Internet's traffic. Global communication works because thousands of these decentralized nodes independently calculate optimal paths for every single packet that arrives at their interfaces. The router bases these calculations on its routing table. Stored in high-speed RAM, this dynamic map contains the best-known paths to reachable destinations, and a router consults it millions of times a second. This flowchart illustrates the exact decision process. When a packet arrives, the router first checks if the destination IP matches a network that is physically connected directly to one of its own interfaces. If it is not directly connected, the router moves down to search for a remote network match. It uses a principle called the longest prefix match, comparing subnet masks to ensure the packet is directed through the most specific, granular route available in its table. If no specific match exists for the IP address, the router relies on a gateway of last resort. This default route acts as a failsafe, typically handing the packet off to an upstream provider or edge router. The entire purpose of this logic tree is simply to make one localized decision, identifying the single physical exit interface the packet must be shoved out of to reach its next hop. The stability of the global internet relies on the absolute precision of this localized memory lookup process, executing flawlessly, hop by hop, across the world. The most basic way to populate that routing table is through static routing. Here, a human network administrator manually codes the exact path a packet should take to reach a specific destination. Using a command line interface, the administrator types a command like IP route, explicitly linking a target network to a specific next hop IP address. Because the route is hard-coded, this approach consumes 0 CPU cycles for calculation and wastes no bandwidth on route advertisements. The path is predictable and secure from automated tampering. This makes static routing effective for small stub networks with only one exit point, or for defining the perimeter of a secure gateway. But this rigidity creates a scaling problem. If a physical failure severs the primary link, the router has no awareness of the drop. It will continue forwarding packets into the dead interface, creating a digital black hole. Traffic will drop indefinitely until a human logs back into the router, deletes the failed route, and manually configures an alternative path. To scale beyond a single building or a handful of nodes, networks must abandon the zero overhead efficiency of static routes. They have to trade CPU power and bandwidth to run algorithms capable of sensing physical changes and adapting to them automatically. This automated adaptation is driven by dynamic routing protocols. These are software agents running continuously in the background, consuming router RAM and CPU to exchange topology updates across the network. The earliest and mathematically simplest of these are distance vector protocols, a category that includes RIP and EIGRP. They rely on the Bellman-Ford algorithm to evaluate paths based on specific distance metrics. For RIP, that metric is a simple hop count. For EIGRP, it is a composite of bandwidth and delay. To share data, a distance vector router takes its entire routing table and broadcasts it directly to physically connected neighbors. Those neighbors merge the data and pass the expanded list down the line. This is routing by rumor. A router relies strictly on distance calculations from immediate neighbors, treating everything beyond one hop as a black box. Because they only know what their neighbors tell them, these protocols are vulnerable to routing loops. If a distant connection drops, incorrect rumors about the dead link can bounce back and forth between nodes faster than the network can correct them. The Bellman-Ford approach requires very little computing power, but relying strictly on localized trust prevents a router from ever verifying the true global topology it operates within. To solve the information gap in distance vector logic, modern enterprise networks utilize link state protocols, such as OSPF and ISIS. A link state protocol flips the data sharing mechanism. Instead of handing a complete table to one neighbor, a router broadcasts a tiny packet containing only its direct connection status to every single router simultaneously. These link state advertisements are collected and aggregated in RAM, constructing a complete 3D map of the network topology. With the full map assembled, the router deploys a heavy mathematical engine, Dijkstra's shortest path first algorithm. It runs independently on every router CPU, calculating the absolute shortest cost path through the database graph to every destination, bypassing congested links. When a physical link is severed, the network experiences convergence. New advertisement packets flood the zone instantly. The CPUs trigger Dijkstra to recalculate the map, and routing tables update in milliseconds without dropping traffic. Link state routing achieves high resilience by taxing the hardware. It trades massive bursts of CPU and RAM utilization to guarantee a deterministic, mathematically verified view of the network. To understand how these protocols function at scale, we have to look past the individual router and toward the administrative structure of the Internet itself. The Internet is divided into massive administrative zones called autonomous systems, large clusters of routers operating under a single organization, like an ISP. Inside these boundaries, administrators deploy interior gateway protocols. Both distance vector and link state algorithms belong to this category. IGPs are locked within their specific autonomous systems because they are designed for raw computational speed and rapid convergence inside a trusted, controlled perimeter. There is a hard mathematical ceiling here. If Dijkstra's algorithm attempted to map every active router on the public internet, the RAM and CPU requirements would exceed the capacity of every physical device on Earth. This is why the global network must be partitioned into the autonomous systems we see today. This partitioning creates a final architectural problem: how to interconnect thousands of disparate, untrusting autonomous systems across the globe without overwhelming the hardware. This requires an exterior gateway protocol. Today, the Internet runs entirely on one, the Border Gateway Protocol, or BGP. BGP is a path vector protocol. Instead of mapping individual routers, it maps paths between entire autonomous systems. BGP's core metric is policy, not speed. Organizations dictate routing based on economic agreements and security filtering, even if it forces a physically longer route. The complete architecture of network routing relies on specialized tools at every layer. Manual static routing secures the rigid edge, fast converging IGPs optimize the internal core, and policy-driven BGP connects the global clusters. The global internet functions through this hierarchy: localized hardware decisions and policy-based exchanges across administrative borders. Routing is the coordination of these protocols, calculating path logic millions of times per second to maintain the constant flow of traffic across the globe.